Hello, I'm here today with my partners Justin and Matthias to explain to you the basics of Young's double-slit experiment. In the 1800s, people had thought that light was a particle due to Newton's century-old work on optics. Later, Einstein's work with the photoelectric effect also backed up the particle theory. We know now that light is in both respects a wave and a particle, but let us observe how the world came to this conclusion. For us to discover the reasons for these answers, we must first analyze the properties of waves and particles on an everyday scale. If we shoot balls through one slit, it obviously makes one bar on the screen. With two slits, it just makes two bars. Now with waves, a wave projected through a slit will have a band of highest intensity in the center, directly in front, and with fringes on the side that gradually fade. Things get interesting with two slits. Waves in a double slit experiment show an interesting pattern of alternating on and off spots, like a series of bands. Young devised a clever way to test this theory using the double slit experiment. If light was a particle, it would have two bands, like the ball shot through two slits. If light was a wave, it would show the interference pattern that waves show. We conducted this experiment and saw this. This shows the interference pattern of waves, making light a wave. However, Justin and Matthias will talk about this later and clear this up.
So when two waves collide or interfere with one another, the waves are added to each other. This phenomenon is called the superposition principle. When the waves are within the same medium, the amplitude of the new wave is the same as the addition of the amplitudes of the two interfering waves. When the crests are superimposed and the troughs superimposed as well, this interference is called constructive. When the crests superimpose with the troughs and vice versa, this interference is called destructive. In some cases, like in ours, when the one interfering wave is the opposite of the other, the waves completely cancel out and the amplitude is zero. When we perform a double slit experiment, we experience an interference pattern. To explain this, we must consider light to be a wave. When the light waves interfere constructively, we see a bright spot in the interference pattern. When they interfere destructively, we experience a dark spot. The band is brightest in the center since it has the highest probability of landing there. The bands out to the side of the center band are constructive because one of the waves is out of phase just enough so that it superimposes. Now what if one photon was sent through the double slit at a time? You would expect the experiment to produce a pattern that consists of two bars. However, when this is done, the photon still exhibits an interference pattern. This brings up the question, how can a photon interfere with itself?
A normal double slit experiment looks like this, with an interference pattern. But when a sensor is used to measure the position of photons, the interference pattern disappears. The photons no longer exhibit wave qualities, but instead act like larger particles. This means that if you shoot photons at a double slit setup and measure position, like which slit the photons pass through, they will stop producing interference patterns, just like larger particles. Just taking position measurements changes the outcome of the experiment. The photons will instead group into two columns on the viewing surface, like this. Even if the sensors don't alter the momentum at all, this effect still occurs. Because of quantum physics, photons move according to probabilities, which is why they appear to interfere with themselves and exhibit wave qualities. Measuring the position right after the slit will collapse the wave function of the photon and reduce the probability of it being in another place to zero and cause it to continue on its measured path. This is why there is no interference pattern after measurement.
This interesting changing property of light due to measurement can actually also be seen with small particles, like atoms. We already know the equation for the double slit experiment. Distance between the slits equals the wavelength multiplied by the length of the setup divided by the distance between the two slits. Louis de Broglie figured out the wavelength of normal matter, not just a special case like light, to be Planck's constant divided by the momentum. This means that technically, all matter has a wavelength and exhibits all the properties of light in the double slit experiment, including the changes from the act of measuring the position in the slit. This is a huge revelation, since this means that all events in the universe are affected by our observation, because in principle, all matter has a de Broglie wavelength.